Hi, I'm Tong from Rutgers,
And I'm Nick Martelaro from CMU.
and we are here to talk about our paper on learning when agents can talk to the drivers using the INAGT Dataset and Multisensor fusion. This is work with our collaborators Stent from the Toyota Research Institute, Jorge Ortiz from Rutgers, and Wendy from Cornell Tech.
In the future, proactive speech agents could be very useful for drivers. However, picking the right moment for the speech agent to interact with a driver can be challenging due to the complexity of the driving environment and the fact that interrupting a driver at the wrong moment could be distracting or annoying. Here's an example of a driver being interrupted at not such a great time.
Is now a good time?
No, making a turn.
Since we can capture various forms of data such as video, car telemetry, and human physiology, we work to build a multi-sensor fusion model that could predict good and bad moments to interact with the drivers based on their preferences and third-party ratings of safety. Using a 4-channel CNN, we were able to achieve a 0.874 F1 score, predicting good and bad moments to interact, and a 0.891 F1 score to predict safe and unsafe moments.
To train our model, we used a subset of 1,915 samples from previously collected data, where drivers were randomly asked is now a good time on a 25-kilometer driving route. They then self-annotated their preferences for interaction by saying yes or no. Each sample includes in-cabin video of the driver with body pose estimation, road video with traffic object detection, car telemetry, and physiological data from the driver. Because prior research has shown that drivers might be overconfident in their decisions when to interact with car interfaces, we also augmented the dataset by collecting ratings of how safe a moment was by asking third-party raters on Amazon Mechanical Turk. 4 Turkers rated the moment for how safe it was to interact with the driver on a 5-point scale. We then averaged these ratings and used those to train a safety model in addition to training a preference model.
Since the dataset contains 22 sensors with different sampling rates, we align and resample to 10 Hz with linear interpolation. Videos were segmented into clips with 6 seconds before the is not good time question was asked. In our dataset, drivers' responses are highly imbalanced with 78% of yes and 22% of no. We adopted SMOT to synthesize new samples for the minority class in the training set to reach an optimal ratio. Here's the architecture for multi-channel deep convolutional neural network, PazNet. Channel 1 takes the road video and extracts spatial and temporal features by I3D inception V1. Channel 2 and 3 take the pre-processed data from physiological sensors and CAN systems. We adopted 2 CNNs as feature extractors, which are able to capture both temporal characteristics and internal correlations among different sensors. Channel 4 uses landmarks of the driver's face, hand, and body, which are extracted by open pulse on videos from face and side body camera. A CNN is used as well for feature extraction. We performed early fusion by concatenation of each features and using a multi-layer perceptron for classification. We combine and compare different feature extraction techniques on both shallow and deep nonlinear models. This table shows that PazNet attains the highest performance on both k-false cross-validation and leave-one subject-out cross-validation by combining all data sources and extracting features separately. Here's the example that our model correctly predicts a good moment to interact with the driver.
Is now a good time?
Yes.
And here is a moment when our model correctly predicts a bad moment to interact with the driver.
Is now a good time?
No. Getting on the freeway.
Because distracting driver at the wrong time could be quite bad, we reweight the classes of yes and no training samples so that we create a more conservative model that can reduce false positives to 0, meaning the agent does not predict a good moment to interact with the driver when the driver says no. But this graph shows that even our most conservative model still gives an average 24 opportunities to interact over a 50-minute drive, which we believe that would be still sufficient for real-world systems.
We then retrained PazNet to predict if the moment was safe or not based on the third-party annotations. Using the safety model and the preference model together, we then build a composite system that predicts first if it's safe and then moves on to predicting drivers' preferences to ultimately make a final decision on when to interact. Here's an example of when our model predicts unsafe and the driver says no.
time?
Right to merge onto Father Junipero Serra Freeway towards San Francisco.
Still, there are moments where the driver may believe that they can interact, but our model predicts it is unsafe.
Is now a good time?
Oh yes, I'm just making a turn.
In these cases, we would not have the agent interact. While this reduces interaction opportunities, it does not eliminate them because there are still many moments that are both safe and preferable. In summary, our research proposes a multi-sensor fusion network to predict when to speak to drivers based on their preferences and notions of safety. To support this effort, we augmented our data with third-party annotations of safety, and we make this available to the research community. Finally, we show that fusing automotive, physiological, and visual streams and conservatively tuning our model allows us to develop an agent that achieves better predictive performance in choosing opportune moments to interact with drivers.
You can find more information and the link to the Is Now a Good Time dataset on our project page. Please feel free to reach out to us if you are interested in using the data, learning more about the modeling approaches we use, or thinking about how proactive speech agents can tell when to interact with the people based on contextual factors.